Okay, so we are absolutely surrounded by computers, right? They're in our pockets, on our desks, even on our wrists, and they all speak the same language, zeros and ones. But what if I told you there's another kind of computer out there, one that thinks not in code, but in waves? Today, we're going to explore the fascinating tale of two computers, analog and digital. Look, you know the digital computer inside and out. It's what you're using right now. It's fast, it's powerful, it's super precise. But before all of this existed, there was an ancestor, a completely different way of thinking about calculation that, believe it or not, paved the way for everything we have today. So first up, let's pull back the curtain on this other computer. It's kind of the forgotten variant that worked in a way that might seem totally alien to us now. So let's meet the original, the analog computer. Get this, it didn't think in steps, it thought in waves. It didn't count, it measured. So what on earth does that actually mean? Well, an analog computer represents information using continuous physical things like voltage or pressure. And the key word here, the one to really latch onto, is continuous. No breaks, no steps, just smooth, flowing values. Here's a perfect way to picture it. Think of a dimmer switch for a light. You can slide it smoothly from totally off to full brightness, and you hit every single little point in between, right? It's not just on or off, it's a whole continuous spectrum of light. That's analog. And these machines really had their moment. Back in the 1950s and 60s, analog computers were absolute workhorses in science and industry. They were used for everything from simulating flight paths to controlling huge industrial processes. You've actually seen this kind of analog thinking your whole life. A classic mercury thermometer where the red line rises smoothly, the needle on a car's speedometer, the hands of a clock just sweeping through time. Yep, all of those are analog devices, measuring continuous change in the real world. But here's the catch. For all their elegance in measuring the real world, analog computers had some really serious problems. They were often slow, not super accurate, they could barely store any information, and they were incredibly difficult to program for new tasks. Something had to change. A new solution was needed. So what was that solution? Well, enter the digital computer. It took a totally different path by breaking everything down into tiny, super precise pieces. A digital computer works on what we call discrete signals. Now, discrete just means separate and distinct. It represents everything, numbers, text, you name it, as a long string of binary digits, or bits, the famous language of zeros and ones. And this just illustrates it perfectly. I mean, this binary code might look like total nonsense to us, but to a digital computer, it's a crystal clear instruction. In this case, it's just the word hello. Every single piece of information on your phone or your laptop is stored just like this. So, let's go back to our light switch analogy. If the analog computer is that smooth dimmer switch, the digital computer is just a simple regular light switch. It only has two states, on or off, 1 or 0. There is no in between. And you know what? That simplicity is its greatest strength. It's precise, it's clear, and it's perfectly repeatable every single time. And its whole process is just beautifully straightforward. It takes in data as binary input, it follows a set of instructions to process it, and then it gives us an output that we can easily read on a screen. Simple, incredibly efficient, and unbelievably powerful. And the result of that? Well, this technology is now the absolute bedrock of our modern world. From the smartphone in your hand to the laptop you work on, every single one of these devices thinks in that clear, precise language of digital code. So this brings us to the main event, the digital takeover. Why did this new way of thinking not just compete with analog, but almost completely replace it for pretty much everything we do? Let's put them head to head. Okay, so the most crucial point to get is their fundamental difference. Analog represents reality with a continuous, flowing model. Digital, on the other hand, represents it with discrete, countable symbols. And that one little difference changes everything. And when you line them up side by side like this, the winner becomes pretty obvious for most applications. Digital computers are just vastly more accurate, they have enormous memory capacity, they're more reliable, and they're so much easier to use. On almost every key metric for modern computing, digital just blows its ancestor out of the water. Let's just zero in on one of those for a second, speed. The difference we're talking about here isn't small. It is a colossal, mind-boggling gap. The processing speed of digital computers allowed for calculations and tasks that were, well, they were simply unimaginable on the old analog machines. But maybe the most important advantage was this: digital computers are general-purpose machines. An analog machine was often built to do one specific thing. A digital machine, though, can be anything you want it to be. A calculator, a word processor, a gaming console. All you have to do is change the software. That flexibility is what changed the world. And this quote from our source material really just says it all, doesn't it? For general-purpose applications, digital computers are unbeatable. For the vast majority of things we want computers for, the digital approach isn't just better, it's in a league of its own. But hey, this isn't a eulogy. The analog ancestor isn't extinct, not at all. It's actually found a new life in some highly specialized fields. Because it thinks in those continuous waves, it's uniquely amazing at modeling really complex, chaotic systems, things like weather patterns or fluid dynamics, where the real world doesn't move in neat little steps. So its legacy, it definitely lives on. So yeah, digital computing clearly won the battle for our desktops and our pockets, no question. But here's a final thought to leave you with. In this new age of artificial intelligence, where we're trying to build machines that mimic the continuous, complex, and messy workings of the human brain, could some form of analog thinking actually make a powerful comeback? What do you think?